All right, here we go with our first remote distance learning lesson. We'll see how this goes. So, take a look at the following problem. If I asked you to solve this problem, what would you tell me to do? Pause from dramatic effect. Yes. All right, so you would tell me that we would rewrite 100 as 10 squared, and 10 to the x is equal to 10 squared. Therefore, 3 little dots, x has to be equal to 2. So far, we haven't done anything brand new. We're basically reviewing exponentials, which means we need to rewrite the bases, rewrite the exponential equation so the bases are the same. This is what we did in the last unit. So we rewrite the bases, the exponential equation so the bases are the same. Example, 10 to the x is equal to 1 over 100 implies that 10 to the x is equal to 10 to the negative 2. Therefore, x is equal to negative 2. So that's review. All right. So the question then becomes is, what do we do if I want to say, let's solve 10 to the x is equal to 20? Clearly, there's no way to rewrite 20 so it has a base of 10. Okay, so we need a way to undo the exponential and get x out of being the exponent. Kind of like x squared is equal to 25. So we had to undo the squaring to get the x by itself, and we undo the squaring by taking the square root of both sides. Therefore, x is equal to positive or negative 5. We can't forget both answers, okay? But basically what we're doing is we're undoing the square to isolate the x. So, is there a way to do that? Well, square roots undo squaring, cube roots undo cubing, fourth roots undo raising something to the power of 4. So it just probably holds true that there's something that we can do to an exponential equation to isolate the x. Shocker. That's what's called a logarithm. And basically a logarithm is just the inverse function of an exponential, and it allows us to solve exponential equations for the exponent. Notation or shorthand, you will hear them referred to as logs, and not meaning things that you get when you cut down a tree. These are logarithms. They are the inverse function of an exponential. And as you can pause the video, I'm going to move on to the next slide. So if you're writing things down and you're taking notes, pause the video, write the things down, and then move on to the next one. So this here is an example of an exponential. So the red function here is y is equal to 10 to the x. Nothing new. We could input the x value 0, and 10 to the 0 is 1, so that point is noted. So inverse functions, if you remember, are reflections about the line y is equal to x. Because in order to find an inverse, basically you have to switch x and y and then resolve the equation for y. So you may have done some of those with linear functions, with quadratic functions, but for our intents and purposes, we're going to focus on the exponential function. So the red graph, the red one is the equation y is equal to 10 to the x. The blue graph, that's what I'm getting to, the blue graph is the log of x base 10 is equal to y Actually, scratch that. It's the log of y is equal to x. Okay? So this log function, it's the inverse of 10 to the x. Okay? So we're going to be playing with that. We're not looking at the graphs of these quite so much right this second. We're actually going to look at how we use logarithms, how we use our calculator, what the notation looks like, and then doing some practice with some of the properties of logarithms. So basically what we're doing is we're going over chapters 6A, 6B, and 6C in this video. So notationally, notation of exponentials, I'll stick with red for exponentials. The notation for the exponential a to the x is equal to b isn't anything new. It's what we covered in the last unit. But the new notation is that the log of b with base a is equal to x. So again, a logarithm, when we take the logarithm of a value, we get an exponent. So x is the exponent. Okay? So again, these two equations right here, these two equations are the inverses with the variables in the exact places where they need to be. So notice, a is the base, x is the exponent, and b is your answer. So when we take the logarithm of something, we take the logarithm of your answer with base a and get our exponent as the result of the logarithm. So this is just notation. Now, notationally, we actually will use many different numbers for a base, but there are some common bases. Not like first base, second base, third base, or home. But the common bases that you'll see are base 10 and base e being the natural number that we talked about in our exponential unit. We're going to come back to e later, but today we're going to focus on base 10 and other bases. But the common bases are base 10 and base e, and those are the two bases that exist on your calculator for actually doing calculations. So, what that would look like for base 10 would be the log of b is equal to x. We don't write base 10. We just leave it blank. So, go ahead, pause the video, and get out your graphing calculator. Okay, so hopefully you paused the video, you got out your graphing calculator, but let's talk about logarithms in base 10. Base 10 is one of the most common ones, but let's say we were going back to that original function that I said, all right, what do we do when we can't solve 10 to the x is equal to 20? Well, then I'm going to go ahead and I'm going to rewrite it using a logarithm. So, we take the answer and take the log of the answer. So it's going to be the log of 20, base 10. We can see that the base is right there. I would normally write it here, but again, we don't need to write base 10. We can leave that blank. And then it's equal to our exponent x. So there's your exponent x. And that's what we actually rewrite. So now it's just a matter of literally typing it into our calculator. So if you take a look at your calculator, and probably would have been helpful if I had taken a screenshot of the calculator and posted it. But on your graphing calculator, you will see, I believe, there's an x squared button. And above it has a root. And there's a 10 to the x. And above it, there's a log. And then there's an e to the x button, and above it is ln. So this is the one that you're going to actually use. So you're going to need to use your second, and we're just going to do second 10 to the x, because that's log, okay? Second 10 to the x of 20, and you're going to calculate that and get a decimal approximation. I don't want to stop recording, but I didn't bring up my calculator. So I think I can actually I'm still screen sharing with you guys. This is very, very interesting for me. Where's my calculator? I swear I have a calculator on here. Maybe. Is it in a folder? No. I guess I don't have a calculator. How does one not have a calculator on an iPad? It's very interesting. No calculator. Actually, let's look for a calculator. Seriously, there's no calculator on an iPad? Alrighty. So, that's okay. So that's gonna be how we actually calculate that. And then you can try a few more on your calculator. Try log of 3 and log of 0.008 and get those two decimal approximations as well. Just make sure. But this is the button that you're using on your graphing calculator for that. So that's all good and well, but what do we do if we don't want to use a calculator? Because that's something that I'm going to ask you guys to do, is how do you do these without using a graphing calculator? So first of all, take a look at these two problems, log of 10,000 and log of 1 divided by the 4th root of 10. And let's think about how we could actually use, or not use, a calculator to rewrite these logarithms as exponentials. First of all, taking a look at number 1, there's no base written. So if there is no base written, what did we talk about? We talked about the fact that the base is base 10. So the first thing that I always do when I'm doing these without a calculator and actually asking you to rewrite them is I'm going to set it equal to some value x. So now I have it set up as an equation, and what I can do is I can go back to my notation and rewrite my logarithm as an exponential. So hopefully not making anybody dizzy. So what's the base? Well, no base is written, so that means base 10. My answer is an exponent, and the answer is equal to 10,000. Now we just apply what we learned in our last unit, which is that 10 to the x is equal to 10, 4 zeros, so 10 to the power of 4. Therefore, x is equal to 4. Okay, and we can look at the next one. Take a pause the video, see if you can rewrite number 2 as an exponential. Okay, so hopefully you took a pause and you attempted it. I'm going to set it equal to some value of x, because that means 10 to the value of x is equal to 1 divided by the 4th root of 10. So now I want to rewrite it in exponents because I don't like that radical. So I'm going to rewrite this as 1 over 10 to the 1/4. I need to make it so it has a single base of 10, so I'm going to pull my 10 to the 1/4 to the numerator, and now it's 10 to the negative 1/4. So 10 to the x is equal to 10 to the negative 1/4. Therefore, x is equal to negative 1/4. Okay, so I did go back and I actually went downstairs and I actually grabbed my calculator. That's why I think I sounded out of breath. And I just wanted to verify log of 20 is equal to 1.301. Log of 3 is equal to 0.477. And log of 0.008 is equal to negative 2.097. And in doing that, I did actually realize that this and this are upside down. The button itself actually says log with a 10 to the x as the second key, and it actually says ln and with e to the x as the second key. So I actually have them upside down. We don't actually need to take the second. We just need to type in the button. Log of 20 is equal to 1.301. So on our calculators now, we can take a tan and we can go log rolling. I know, PK jokes. All right, so rewriting logarithms as exponentials. We don't just need to use base 10. We could use whatever base there is. Example, let's say I wrote log of 10 base 3 is equal to x. I could rewrite this one as 3 to the x is equal to 10. And we know 3 squared is 9, and 3 cubed is 27. So that means x is probably somewhere between 2 and 3. All right. So this one we're actually not calculating yet, FYI. We're not talking about how to find this one on a calculator yet. We could do this one because we could actually plug it into the graphing calculator. We could graph it and find out where, what value of x gives us an output of 10. We could graph it into y1 and y2 and actually figure out where they intersect, and that would actually give me the value of x. There are other ways to do that, and we'll talk about those in upcoming videos. All right, laws of logarithms. Remember that the output of a logarithm is an exponent, so therefore these laws of logs kind of work with exponentials in a way. The first law is number 1, that, and I'm going to write them all with base 10, but they could be with whatever base, but the log of m plus the log of n is equal to the log of m times n. So if I multiply m and n, I can separate them into the sum of 2 logs. Rule 2, log of m minus log of n. Anyone want to take a guess? If we add them together, we multiply. So if we subtract them, you are correct. We are going to divide m divided by n. The third rule, or the third law, has to do with exponents. And let's say I have the log of some value b to some power of m. That means I can rewrite this as m times the log of b. So it's kind of like that power rule that we use with laws of exponents, but it's kind of like that power rule, okay? So remember that a log is a function. So it's kind of like a square root symbol. It's kind of like something to the power of 2, etc. It is a log function that we need to be able to use. There's one more. It's not necessarily a law, but I do want to show it to you because I want you guys to remember this, is that if I take the log of b with base b, my answer has to be 1. That's because b to the 1 is equal to b. Okay, so when we look at integers, we can rewrite integers, specifically positive integers, as logarithms. Okay, so I have a series of 1, 2, 3 slides of examples. What I would like you guys to try to do is to pause it, try the example, and then watch the video for the solution. That would be my suggestion of how you should probably attack these. So the directions for these ones are to rewrite as a single logarithm or as an integer. So I'm going to take them piece by piece. Okay? Notice they have the same base, because that's the only way these things are going to work is if they have the same base. So both of them have base 5. The operation between the two logarithms is subtraction. So that means I'm going to rewrite them using not a multiplication, but division. So log base 5 of 100 divided by 4, which is log base 5 of 25. Now, 5 and 25 kind of have a relationship. In fact, 5 squared is equal to 25. Therefore, the log of 25, base 5, is equal to 2. All right, so what do we do if there's 3 parts? Well, we're going to take it part by part, order in order. What's the base? And do all 3 logs have the same base? Yes, they do. They are all base 10. So the first 2 logs I'm going to rewrite as the log of 6 divided by 2. And then I still have plus log of 3. So I'm going to finish this log of 6 divided by 2 and rewrite it as log of 3 plus log of 3. So now we're going to multiply inside. So we're going to do log of 3 times 3, which is equal to log of 9. And on this one, there is no way to take 10 to some power and actually get 9 without it being some funky decimal approximation. In fact, I could actually use my calculator, type in log of 9 and get 0.954, which makes sense because 10 to the 1 is 10, so 10 to something equals 9 needs to be a little less than 1 exponentials. All right, what about these 4? Well, the first one, again, don't forget, pause, try to do it, try to manipulate, try to see what you can do. This first one doesn't have a log, so I'm going to leave my log of 7. What's my base? You are correct if you said base 10. Hopefully you're answering me and my questions, because that would at least make this feel a little bit better than me teaching to myself in my bedroom so that nobody distracts me. But, all right, so log of 7 plus 2. Well, we talked about one of the rules saying that the log of 10, base 10, is equal to 1. So that means I could rewrite 2 times log of 10. Now, if you don't believe me, type in log of 10 into your calculator, and it should give you the value of 1. Well, that means now I can use my exponential laws, and this number that's being multiplied by the log can become the power of the 10. So I'm going to rewrite this as log 10 to the power of 2. So that 2 becomes the exponent, which is kind of cool because we have log of 7. Now we have the same base, same log, or logs with the same bases being added. So now that we are adding them, we can rewrite them as a multiplication problem. In fact, log of 7 times 10 squared is the log of, yep, you got it, 700. So let's try the next one. Where's my 5 gonna go? It's going to go become the exponent of the 2. So it's going to be log of 2 to the 5th plus log of 3. Multiplier addition means that we're multiplying, so we're going to do log of 2 to the 5th times 3. And 2 to the 5th is what? 2 to the 5th is 32. So we're actually doing the log of 32 times 3. 90 plus 6 is the log of 96. And again, neither of those can be simplified any further. All right. This next one. There wasn't anything that divided logs. My rules didn't divide logs. The rules divided what we're taking the log of. So this one is a little different because it's not actually dividing the logs, is it? But I see that too, and wait a second. The log of 8 is actually the log of 2 cubed divided by the log of 2. But where do we take that exponent? We take that exponent and put it in front of our log. So we're actually going to say 3 log of 2 divided by log of 2. And we all know what can we do with the log of 2? They will divide out. And what are we left with? You got it. We're left with 3. All right. Next one. 1. What's my base? My base is 10. So I'm actually just going to say this is the log of 10. Minus log of 2 cubed plus log, not 10g, sheesh, PK, plus log of 20. First 2 means division. So we're going to do log of 10 divided by 8 plus log of 2, which now it's addition, so it becomes multiplication. Log of 10 over 8 times 2, which simplifies into log of, 2 cancels 8 4 times. This becomes 5, this becomes 2. Log of 5 halves. And I'm going to leave it as the log of 5 halves. Okay? So hopefully you tried these. Press pause. Looked at it, press pause, tried it, and then actually watched the rest of the video. So, I love these. These show that because I'm telling you that this is true. So since I'm telling you that this is true, I want you to manipulate so that you can show that one side of the equation is equal to the other side of the equation. Those of you at Algebra 2 Pre-Calc, these are trig identities. All of those trig identity questions that you did last year are show that questions. Meaning we're not going to work on both sides of the equation at the same time. We're only going to work on one side of the equation at once and manipulate it until it looks like the other side. So, in that being said, which side do you think we should work on? The log of 5,000 or 4 minus log of 2? Dramatic pause. Awesome! I'm so excited that y'all decided that we're going to work with this 4 minus log of 2. Now, we're going to use those previous things that we just did where we took some of these whole numbers and changed them into logarithms. So I'm going to rewrite that 4 as 4 times the log of 10, because that's just 4 times 1, minus the log of 2. Now I'm going to rewrite as log of 10 to the 4th, those power rules, minus log of 2, which is log of 10 to the 4th is 10,000. That was part of one of the other problems, minus log of 2. Subtraction means we end up doing division. So we're going to do 10,000 divided by 2, or the log of 5,000. Therefore, we showed that the left side does indeed equal the right side. So we've done basically our proof that this is true. So this is just continuing like the math that you guys have done. You did proofs in geometry, where you worked with one side and you worked with the other side and you use the rules and you use the laws to say that they're true. So anytime IB asks you a show that question, they're actually asking you to prove something, but it's not as sticky as those geometry proofs where you have to say, okay, I know this angle is equal to this angle by vertical angles. And I know this angle is equal to this angle because we've got alternate interior angles are congruent. And this triangle is congruent to this triangle because of SAS. It's not as in-depth as that. So what you're doing is you're doing the math and manipulation using things that are true. So again, we use these laws. So this first one, by introducing this log of 10, that was basically what I said was law 4. And then, in order to get this piece, that was basically rule 3. Then, to take and get this piece, that was basically law 2. So, I use the laws, right? We use the laws of logarithms, but it's not as sticky as a proof because we don't actually need to say, I'm doing this now, and this is my reason. I'm doing this now, and this is my reason. I'm applying them mathematically to show that the right-hand side of this equation does equal the left-hand side of the equation. And that's what I think is so cool about these. Now, what I will tell you as far as IB is, you need to make sure you know these log laws. You're going to use them. I have absolutely no clue if they're on the formula sheets. If somebody wanted to check and post a note to everybody, that would be awesome. I am going to actually have to find a formula sheet because I don't think I brought one home with me, and obviously I can't go to school. So this is the unit, or this is the lesson for this week, starting on March 30th and running in through April 6th. I did choose, it comes out to 34 problems. I'll tell you, I counted them, but a lot of them are rewriting the exponential, typing things into a calculator. Part C are your laws of logs. So that's actually where you're actually doing practice with this. Part B is where we're doing logs with bases other than 10. And then part A was logs with base 10. So a lot of them are just rewriting exponentials, but those are the problems that I want you to do. Once you have them done, all I'm asking you guys to do is I'm not going to use a Google Doc. I think I'm just going to go ahead and use a assignment on Schoology. And all I want you to do is to take a picture of it and upload the picture to the Schoology doc. I'm still playing with that and trying to figure out what's the best way. So if I give it to you in a way and it doesn't work, please let me know ASAP because it didn't work. We'll give it a try. So I will actually post all of my notes to Schoology in addition to the videos. So you don't have to go back and watch the video 18 million times and listen to me talk because I wouldn't want to do that either. So hopefully you guys are all doing well. I miss you, and teaching this while recording it is really, really, really weird. And I'm probably sitting here in my bedroom using hand gestures and pointing to things. And so hopefully this makes sense. Like I said, I am also going to upload a number of things that Mr. DeRay found. There are additional problems there. And then eventually I'll have you do some of the problems on that as well. So if you have any questions, get onto my office hours, ask away. I will have my book. We can look at problems. I honestly think even I have batteries coming for my Surface Pencil. I'm hoping that I can do some of these things with you guys live via Zoom if you guys are having questions. So take care, be safe. I miss you, and here's week 1.